Hello everyone, today I will introduce to you Physics 212 project. It is a Michaelson-Morley interferometer for measuring speed of light during the daily change. If the day changes, as the day progresses, if the rotation of the earth affects the speed of light, then we need to get some phase shift in the interferometer because speed of the light is modified just like putting a gas. However, with the modern physics, this claim is defied, so ether does not exist because speed of light is always constant in a vacuum or in a constant pressured gas chamber. So let's see the experiment details. The experiment is shown in this picture. There's a laser here, beam splitters, splits the beam into two parts. Then they are reflected from two mirrors and combined in the screen. So as you can see from the formulas here, if there's some speed of light changes due to ether, then this speed will result in a time delta like this, and then it causes a delta phi or phase shift, and phase shift is rendered on the interferometer. So how do we set up this experiment? First we need to get some mirrors and beam splitter, of course. So this is a holder. This is a hexagonal shape. There are magnets here. The shape is compressed like this, so magnets are compressed. There's a shear force here plus the magnetic forces, not shear force, this is a compression force in this direction, so that there's an immense amount of friction between magnets, so that if we replace anything like mirror here, then we get very tightly holded mirror like this. And this hexagon is manufactured from PLA in a 3D printer, so this is very massive and does not move with the natural forces. It needs a brute force. It has very high friction. The same setup for the beam splitter. Beam splitter is a slider from a microscope. The slider is also put onto those magnets, and there's a wooden frame because 3D printer ran out from the service. And we have a green laser. This is a class 3B laser, and this is very dangerous to work with. It has 50 millivolts. The beam is visible through the air, and it should be handled properly and with the immense care. The same magnet structure is in here. Also, those woodens are held tightly. So let's see the entire setup. The setup is put on a cross. This is a balsa wood cross and all other components here. Then we get interference pattern over there. Then we record this with camera. So how do we verify if it is an interference? Firstly, we shine the laser and two beams are come together on the beam splitter. If on the beam splitter there are one dot only, then okay, that's done. And then we put object here and we gradually put this back to up to a few meters. Then we need to see this interference pattern. So how do we verify it is real interference from two of them, not a masquerade from some diffractions or a fingerprint? So we put a opaque object on this mirror so that this path is blocked. Then we get single path image right here, and then we do the same for here, and we also get this image again. This means that if this thing does not move, because those are very stiff and they doesn't move. However, if we take all the opaque objects again and make this bipath interference. Then we need to get this, and those fringes need to vibrate. So this pattern does not vibrate, but this one vibrates, and it's correlated with our movements. If we jump in the room, then they wobble crazy fast. Anyway, let's continue. After the interference pattern is recorded for an hour, yet we need to see 24 hours of changes. We get 2000 frames of images, and we took a time lapse for 1 hour, and frame spacing is 2 seconds. This means that we have 0.5 FPS, and we get images like this, 2000 these images, and then we need to verify if there is a 24 hours of variations on this. So what we do 2D, we firstly do a spatial filtering on the images so that we remove all fine details. Fine details are vibrated very quickly and they are not stationary for a long time, so we eliminate them. Also, we need to perform cross correlation with different waveforms so that we need to check if there is a spatial 24 hours of change, or the 24 hours of change is just within the noise floor. So to check if we perform 2D spatial filtering, like here, this is the filtered spectrogram. We only look at those parts of the spectrum, 10 pixels per cycle. So this is the spatial filtered image, and then we stack all of 2000 frames. Then we perform cross correlation with Gabor wavelength. This is the Gabor wavelet. It's the Gaussian enveloped complex exponential. What is the purpose of Gaussian envelope? Because we also put Gaussian envelope to these images through the time axis. So how do you imagine it? So we have this image in the first time and this one the second time. So we multiply this with 0.1 and this one with 0.2, so that this part of the image has, this part of the time series have very small amplitude, so that if the end of the sign is large, then this one is multiplied with small, so that this large part is eliminated. So we only look at central parts for harmonics. What does it mean? You can also visualize it with convolving the spectrum with Gaussian so that you get sharper peaks. So it is just a way to eliminate spectral leakage. There is no frequency loss, just eliminating spectral leakage at boundaries. You can check FFT windowing for this. And we have Gabor wavelength here. We apply cross correlation for 1 to 48 hours with those Gabor wavelets, and then we get this curve. This is the cross correlation amplitudes of each wavelet with given fundamental periods, so that you can see that 24 hours has fairly low amplitudes, so that this is heavily buried into the noise. So there is nothing special about 24 hours of period. Consequently, this means that the speed of light does not change over 24 hours, or at least it's not detectable by our current equipment and processing. So the problem we encountered processing is that this thing shifts through the time. However, this is not problematic because this shift is just a phase modulation in the spectrum of the image, to the spectrogram of the image. So it's not a problematic because cross correlation does not care phase in this time. It doesn't only looks, but actually it's more sensitive to amplitude of the spectrogram images, so that even though its phase changes, it does not change the sum of the cross correlation, so that's not a problem for this. Thank you for watching.